Hello, my name is Cesar and I'm in charge of the risk analysis and the communication and data handling subsystems. Also, I have helped in the design of the thermal control of the satellite.
Hi, I'm Jonathan, and besides the thermal control, I've been in charge of the design of the orbit and the ground segment.
My name is Fernando. I was in charge of the configuration subsystem, the ITM file, and work with Gema in the power department.
Hi, my name is Gema Paricio. I am the system engineer of the StarWorms team, and I collaborated with Fernando to design the power subsystem, and I also worked on the ADCS subsystem.
The StarWorms team used meeting minutes and schedule diagrams such as PERT and Gantt, as well as a Google Drive as a virtual CTF to accomplish all the objectives. The objective of the NANOSTAR project is to test the behavior of the Roscoe worms at the zero gravity of space. The main advantage of this organism is that it can be the answer to recycle CO2 and produce oxygen during space missions. This imposed one of the first requirements of the project, a payload in the shape of an L that weighs 7 kilograms and must be fit into the satellite.
The selection of the orbit was the first thing that should be done, as its parameters would affect all the rest of the subsystems. The possibility of defining a mission in which there was no type of eclipse was considered, since this would be a great simplification in the design of the subsystems. Due to the fact that an orbit of these characteristics will have almost static conditions throughout the mission, a sun-synchronous orbit of Dundas was chosen. This made only possible to have an orbit without eclipses for around 3/4 of the year. During the remaining quarter, there will be eclipses around the north pole of the Earth. These eclipses would be the Earth ones, but moon eclipses could also affect it. From here, keeping the parameters of the orbit invariable, two design options have been considered. First option is launching to a sun-synchronous orbit in which the time of passage through the first descending node is 6 o'clock am, regardless of the date of the year. This option implies that if the satellite is not launched on an optimal date, it will be affected by eclipses. Designing the satellite to withstand these conditions, the number of suitable launches will be much greater, as the positioning requirements would be less restrictive and the launch window wider. The second option is choosing the time of the first descending node depending on the date of the year in which the launch is carried out, to avoid eclipses during at least 3 months. In this way, an inter-launch window could be achieved if the appropriate launch is selected, taking special care to launch at least 3 months before or just after lunar eclipses, as these ones cannot be avoided. By choosing this option, the power and the thermal control subsystems would be simplified, and both the cost and the risk inherent in these subsystems could be reduced, in exchange for limiting the number of available launches and reducing the launch window. The choosing option is the second one, so let's summarize. If the passage time through the first descending node is selected, orbits without eclipses could be obtained throughout the year. Although this option was the most interesting one, the StarWorms team decided to be conservative and considered not being able to choose a launch with such specific characteristics as a very likely risk. Therefore, the power and the thermal subsystems had to be designed in order to withstand eclipses, even though the nominal mission is established to not have eclipses at all. It was convenient that the accesses were constant throughout the days, so the trace should be repeated every 24 hours. The altitude of the orbit that meets this condition is 560 kilometers. At that altitude, a spacecraft would decay about 20 kilometers every 3 months. Consequently, the initial age of the project was established at 570 kilometers, so the nominal altitude is reached at the middle of the mission lifetime. Since the ground segment should rely only on the tracking stations of the ESA network, only 5 locations would be suitable to serve as a mission ground stations. Of the remaining suitable ground stations, the one with the highest minimum access times is NANOSTAR in Australia, so it will be the one chosen to serve as a ground station of the mission.
In order to choose an onboard computer, the first step was to calculate the total amount of data that the payload would produce in one day, taking into account that the pictures and the videos were taken in high resolution. Later, the requirement was established into 550 megabytes per day. The team decided to stay in the same onboard computer, which would allow to store almost 2 weeks of data and thus reduce the risk of not being able to communicate during a period of time. For the design of the communications link, the first step was to identify the data rate using the total amount of data produced and the access time. This, considering the ground station, made the team choose X-band for both uplink and downlink communications. Once the band was fixed, an antenna and a transceiver were chosen from CODs, considering their characteristics, the ground station, and losses by, for example, temperature, noise, and free space. The power margin was calculated both in uplink and downlink cases. As both margins are large positive numbers, good communications can be guaranteed.
In any space mission, an attitude determination and control system is needed. In this project, the ATCS system is of vital importance. Since the mission incorporates living organisms, an active attitude control is necessary to provide stability control. The ATCS must be able to keep the spacecraft below a maximum angular speed of 3 rpm for no more than 10 seconds. In addition, communication system requires an aiming accuracy lower than 0.5 degrees during the connection time. As explained before, the chosen orbit for this mission is a low Earth orbit, so it is necessary to study the possible disturbances that it introduces in the attitude motion of the satellite, because ATCS must provide an additional torque to overcome them. The most important disturbances are those caused by gravity, solar radiation, pressure, and aerodynamics. Also, these are several orders of magnitude smaller than those necessary for motion, and this makes them irrelevant to size the attitude control. According to the requirements, due to the impossibility of uncontrolled rotation by the presence of living organisms in the payload, passive control is discarded. This need for 3-axis stabilization and the precision required by grounding in data transmission time leaves reaction wheels as the best option of actuators. To recognize the position of the vehicle, there are several sensors that provide an interpretation of the vehicle orientation. Since chosen actuators are mechanical, magnetometers have been discarded in order to avoid mixing different type components. According to this, the best option is to incorporate the following equipment: a star tracker to mitigate risks and further guidance, 2 sun sensor pack system on the lower and upper sides of the satellite to ensure the position and orientation of the satellite during the daylight period, and an IMU to ensure the attitude determination in case of eclipse. Power subsystem determines the amount of energy needed for all the operation modes of the satellite. Once the nominal operation of the satellite and the power it requires are known, different power modes have been sized to reduce the total area of solar arrays and the amount of total operation power needed. Although the main mission has been designed to avoid eclipses, the StarWorms team has decided to parameterize the power subsystem to withstand them. As a result, 6 modes can be obtained from all the combinations of the use of the main subsystems. It is remarkable that the most energetic mode, the mode E3, requires almost twice as power as mode D2 or mode E1, which are the ones that will be operative during more than 95% of the daily orbits. As a consequence, the strategy followed by StarWorms team has been to eliminate it to reduce the most consuming mode to a level in which it is more similar to the nominal performance of the satellite. The combination of placing a 6U solar panel, 2 3-unit deployable solar panels on the lateral sides, and a battery pack can produce the required energy to fulfill any power mode. What is special about this design is the fact that In order to mitigate the case with eclipses, they will deploy to provide the extra needed energy. The two batteries that this CubeSat design has offer the perfect solution for both the thermal and power subsystems. These are necessary for the peak power in the ideal case of mission without eclipses, for full operation in case of eclipses, and finally offer the dissipation of extra energy to keep the temperature of the subsystems within their limits in the cold case of having eclipses in the orbital periods.
In order to carry out the thermal control, heat flags must be analyzed. The satellite must remain at all times in a specific temperature range. This range was extracted from the ranges of all the subsystems involved. According to power needs, lateral faces were covered by solar panels. As the nominal operation of the satellite is without eclipses, the other two have been decided to be painted in white for lowering the maximum temperature at sunlight. In the nominal case, being at sunlight, the temperature must be under 40 degrees. In this case, heat comes from sun, batteries, Earth in infrared, and albedo. First two sources were easy to calculate as they are fixed numbers. The heat from sun was calculated considering the 6-unit phase that points it perpendicularly, and heat from batteries was calculated from their dissipation when they are charging. Heat from Earth in infrared reaches the satellite perpendicularly at the bottom phase, and as the Earth is much bigger than the satellite and they are close to each other, the heat also reaches lateral faces with some angle as it is shown here. Finally, heat from the albedo should be almost zero as the satellite's orbit is in the plane perpendicular to sun rays. Nevertheless, it was calculated the angle that would reach the satellite after hitting Earth and reflecting, and from that the maximum temperature of the satellite was calculated considering the emissivities of its faces. As temperature is lower than 40 degrees, no radiator is needed. The cold case was easier to calculate as it just considered the heat from Earth in infrared, which is the same as previously, and the heat from batteries dissipation, which is in this case was higher than before. Temperature was calculated with these sources, and it was seen that a heater that dissipates at least 11 watts-hours was needed in order to reach the minimum temperature required. Summarizing, a sufficient thermal control is reached by using the solar panels and white painting in the faces of the satellite during hot case, and in the inside of the satellite, fluxes are controlled using the dissipation coming from the batteries and a heater, which will maintain the temperature during eclipses.
Once all the subsystems were established, the final configuration of the inside of the satellite was decided to be this way. Both batteries, the radio, the antenna, the reaction wheels, and the OBC at the lower units. Payload at the middle top sections, and the star tracker camera, and the IMU on top. Also, the sun sensors are located on each 2U face. According to CubeSat Mechanical Requirements 3.2.9, the maximum weight that is allowed to carry on a 6 unit is 12 kilograms. Gathering all the components from the other subsystems and applying an extra margin, there is still about half a kilogram to get to the limit. This mass margin implies that if some of the elements are rearranged, such as the radio and the IMU for example, there is an empty slot that could be filled with a secondary payload, redundancy, or even the primary payload could be enlarged if the NANOSTAR payload department decides so. There are also available two 1-unit surfaces, one at the top, one at the bottom, that can be used to carry secondary payloads such as antennas or small patches, so any company that wants to test a new component is welcome to join the project. One of the most relevant requirements determined that no alive organism from the payload shall be introduced into any area on Earth during the satellite lifetime. There are some discarded options to achieve that. An explosion at the end of the life would not comply with the CubeSat regulation, and the inclusion of a propulsion system that sends the satellite to a graveyard orbit would require even a bigger CubeSat than an 8-unit because of the extra mass and space required. That is why the team decided that the end-of-the-life strategy would consist of a simple yet effective natural decay to Earth due to atmospheric drag, that depending on the solar activity will take from 5 to 15 years. As soon as the satellite enters the atmosphere, the temperatures of over 1000 degrees will fully disintegrate this 6-unit structure and its components inside.